Okay, welcome back. The next dynamic programming problem we're going to take a look at is called the partition problem. The idea here is that you have a set of items and you'd like to partition that into two sets with equal value. So for example, let's suppose that you've got a bag of coins that you found in the attic and you would like to equally divide those coins between yourself and your sibling, let's say. Can you do that? Can you divide the coins into two bags where each of the two bags has equal value? Now, in a little more mathematical kind of terminology, suppose you're given a multiset that is a collection of integers where you may have multiple copies of certain of these integers. Can you split that into two multisets where each of the values of the two multisets is the same? By the way, both the term bag and the term multiset are used to describe collections of things that may have equal value with one another. If you're more strictly mathematically oriented, you might tend to use the word multiset to describe this. In the artificial intelligence / machine learning community, it's fairly common to talk about this kind of thing as a bag, but the two terms mean the same thing. Okay, so as an illustration, let's suppose that we have a bag containing these coins: 1 cent, 2, 4, 2, 5, 2, 1, 1. And we want to know, can we split that into two subsets, two sub-multisets, where the sum of the values in each of the multisets matches the other? In fact, we can take these coins 1, 2, 4, 2, which sum to a value of 9, and these other coins, 5, 2, 1, 1, which sum to the value of 9, and we have therefore partitioned the multiset. We've used up all the items in the multiset, and the values of each of the two sub-multisets is the same as the other. Now, it's not necessary that the partition that you find has to be unique. In fact, for our example here, if we put 4 and 5 in one multiset, those have a value of 9, and all the remaining values, 1, 2, 2, 2, 1, 1, likewise sum to 9. Okay, so we're interested in the problem of, can we find a partition of the values in this multiset? It's easy to come up with examples that can't be partitioned. All right, so it's not necessarily the case that we're always going to be able to partition some multiset of values. If our values are just these three values, 1, 2, and 5, notice that the sum of those values is 8. Therefore, if we were able to partition those values, each partition would have to have a value of 4. But clearly, 5 is going to have to be in one partition or the other, and 5 all by itself is greater than 4, so it's not going to be possible for us to partition this set of three values into two, well, this multiset of three values, into two multisets, each of which has a total value of 4. Likewise, if you only have one item in your multiset, then it's not going to be possible to partition that. So we've sort of got two questions. Is it going to be possible to find a partition? And if so, what is the value of that partition going to be? Okay, so let's think about, the easy analysis that we can do. We have some set of integers, and we can compute the sum of those integers, and just call that sum m. Then, as I already sort of described here with this example of 1, 2, and 5, if it turns out that the sum of all the values in the multiset is odd, then clearly it's not going to be possible to divide that in half and have two integer multiset sums that are equal. So right away, if we compute the sum of all the items in our multiset and discover that that value is odd, we know it's not going to be possible to come up with a partition. Now, if, on the other hand, the sum of all the integers in S is an even number, then it may or may not be possible to partition that set, that multiset. If it is possible to partition the multiset, then the sum of each of the two multisets has to be exactly m over 2. So, in other words, can we, from this multiset S, all right, I should have called this a multiset rather than a set, can we select items that have a value of m over 2? Let's think back to our knapsack problem where we had items with weights and values, and we were interested in knowing what the maximum value was that we could fit into a knapsack that had a certain maximum weight that it could carry. Well, actually, this partition problem is just a special case of that knapsack problem. Suppose that we define the weight of each item in our multiset to be the same as its value. And suppose we define our knapsack size to be a maximum weight of m over 2. Then we can ask the question, is it going to be possible to find items from the multiset S such that the maximum value we can store in the knapsack is equal to m over 2? If we have a knapsack of size m over 2, or weight m over 2, and the maximum value of items from the multiset that we can fit into that knapsack is equal to m over 2, then we must have found a partition for, we must have found a subset of the multiset that sums to m over 2, and therefore the remaining items must also sum to m over 2. Okay, so we can pose this problem as a 0-1 knapsack problem and solve it that way. Let's do this. All right, now, as a reminder, here's our cell-by-cell algorithm for what's going on in the 0-1 knapsack. We set up a two-dimensional array A in which the rows were the items that we had available to put in our knapsack, and the columns were the remaining available weight that we hadn't yet filled in the knapsack. Okay, each item, the kth item, has both a weight and a value, w sub k and v sub k. In our particular case here for the partition problem, w sub k and v sub k are going to be the same value. Then we figured out that the maximum value we could get from all of the items from 1 up to k, that is all of the rows from the first row up to the kth row, in the column where the maximum available remaining weight was some x, was going to be the value in the same column and the row above in the case where the weight of the current item was too big to fit. That is, the remaining available weight minus the current weight was negative. Otherwise, it was going to be the maximum of the value in that same column from the preceding row, or the value of the current item plus the value from the preceding row corresponding to the column x minus the weight of the current item. Okay, and you can go back and look at that lecture if that's too baffling. All right, so here's what we're going to do. We're going to set up our array where the weights that we can put into our knapsack, and again here we're using our example, this multi-set of values in this order, 1, 2, 4, 2, 5, 2, 1, 1. Turns out if you scramble the order and regenerate the algorithm, you'll still get well, you'll get a partition. It may not be the same partition, but if it's possible to get a partition from this set, you will get a partition no matter what order you have put these values in. But our values in our array are going to be the same as the order in this multiset. Okay, so we have 1, 2, 4, 2, 5, 2, 1, 1. And we're taking those as both our weights and our values for each of those items. Now, in the weight columns, we've already computed the sum of all these values, and we've discovered that the sum of all these values is 18. Therefore, if we're going to be able to partition this collection of values, what we need to find out is, can we create a collection of these items, a sub-multiset of these items that has a value of 9. Now, for a maximum remaining weight or remaining value of 0, we can't use any coins or any of these integers. And continuing onward, if our maximum remaining value is 1, then since our current coin has a weight of 1, we can put a value of 1 in that position. Now, when we do that, when we put our value of 1 into the column for weight 1, we've used up that value now, and so all the remaining columns in that same row are also 1. All right, so using a coin whose value is 1, we can only get a value of 1 if the remaining weight in our knapsack is anything from 1 up to 9. Now, continuing on from there to the next row, once again, if our remaining available weight is 0, then we can't use any values from the multiset, and so the value that we can obtain for a remaining weight of 0 is still going to be 0. For a remaining weight of 1, then 1 minus 2, that is a remaining weight in the knapsack of 1, minus 2, which is the weight of the current item, is negative. So all we can do for a remaining weight of 1 is to use the value that we were able to compute in the previous row, not considering this additional item whose value is 2. When we get to a remaining weight of 2, now our other computation involving the maximum of 2 values comes in. We can either choose the maximum of the row. We can either we can choose the maximum of either the value in the cell one row above our current item, or we can use the value of the current item plus the value in the preceding row that is 2 units of weight less than 2. So in other words, we have a choice between the maximum of 1 or the maximum of 2 plus 0. And of course, the maximum of 2 plus, and of course, the value of 2 plus 0 is 2. So that gives us a value of 2, which again makes sense. If we use the item whose value is 2 and whose weight is 2, we just don't use the other item whose value and weight are 1. Similarly, when we get to the remaining weight in the knapsack being 3, then we can either have 1 as our value, or, and we want the maximum here, we can have 2 plus the value from the preceding row with remaining weight of 1. That is 3 minus 2. And since that gives us 2 plus 1 is 3, that will be our maximum value. Now, at this point, these weights, 1 plus 2, are equal to a weight of 3, consequently, that's going to be the best we can do as far as value for any higher remaining weights. So all of those are just going to get likewise filled in with 3. 3 is the maximum value that we can get just using these first 2 values in the multiset, 1 and 2. Moving on to the third item here, whose value and weight are 4. Well, going up to and including a remaining weight of 3, the best we're going to be able to do is to copy down the values from the previous row. When we get to a remaining weight of 4, then we have our choice between the maximum of 3 or the maximum of 4 plus the value that we had for a remaining weight of 0 in the previous row. That is, we've got a maximum of 3 or 4 plus 0, which gives us a 4. And continuing that theme, that same computation, for remaining weights 5, 6, and 7, we see that we can obtain values of 5, 6, and 7. And I've only shown the highlighted results for remaining weight of 7 here. For a remaining weight of 7, we have the maximum of either 3 or 4 plus this 3. So the maximum of those is going to be 7. Well, at this point now, when we get to a value of 7, we have used up all 3 of the first 3 values. 1 plus 2 plus 4 is a 7, and consequently, we're not going to be able to do better than 7 for these last 2 remaining weights of 8 and 9. And so those also just get filled in with 7s. And now we're on to the next item that we have has a weight of 2 and a value of 2. That all gets copied down. I won't go through the mechanics, but if you walk through all the mechanics, you'll discover that the value of the preceding row is greater than or equal to the value that we can get by using the item whose value is 2. The only changes that we get relative to row 3 are when we get out to a remaining weight of 8, then by also using this item value of 2, we have the maximum of either 7 or 6 plus 2, which is 8. And then for remaining weight of 9, we have the maximum of either 7 or 2 plus 7 is 9. All right, so at that point, notice that we have achieved a value of 9. And achieving a value of 9 was our goal. No matter what's going on with the remaining values in our multi-set of values, we're never going to be able to do a value greater than 9 for a weight of 9. Because remember that the way we've set this up, the weight and value of each of the items is the same. So at this point, because we've achieved our goal, we can just stop and say, okay, yes, we were able to partition that multiset, and we were able to achieve a value of 9 with a knapsack weight of 9. All right, well, that's a lot of arithmetic machinery to be lugging around. It turns out that we can do this more simply by using an array of bools rather than an array of integer values. So let's see how this goes. Suppose the item that we're considering has some value, v sub I. Then clearly we can achieve that value. So in our Boolean array, we're going to have the item values as rows and the achievable values as columns. And so if for item sub I we can achieve a value of v sub I, we'll just fill in the slot in the array with true, okay? So that is, just to pick one, if our v sub I is 4, then clearly we can achieve a value of 4. So we seek out this cell, array sub 4 sub 4, and we fill in a true there. On the other hand, if we go through all of the values that we could achieve using coins prior to, or using values from our multiset prior to v sub I, then any true values here, any achievable values here, will still clearly be achievable whether we use the next value or not. So we'll mark the values that were achievable using the previous coin. The values that were achievable using the previous values are still going to be achievable, and for any value that was achievable for the previous values, we're also going to be able to achieve that value plus, in this example, 4. So we're going to be able, so for any achievable value v sub j, we're also going to be able to achieve a value of vi plus vj, where vi is the current value that we're considering. All right, I think it's going to be easier to see how this unfolds by looking through the examples. So we're going to set up an array of Booleans where the columns are going to be values that we can achieve or that we hope we can achieve, and the rows are the item values, and we're asking, can we achieve a value of m over 2? So consequently, m over 2 is going to be the maximum value that we're going to bother trying to achieve. We're going to start out by initializing all of the cells to false. And then we're going to go through each of the values in our multiset one at a time to indicate which values in that row are achievable from among the various columns. Okay, so our first value to consider from our multiset is 1. And clearly, since our current value is 1, we can achieve a value of 1. Now, having achieved a value of 1, we've used up the 1, and so there are no other values in here that we can achieve. And there's no prior row to consider. So that's all we can do using this first multiset item value of 1. Then, if we now consider the next multiset item value of 2, well, without using the 2, we were able to achieve 1, so clearly we can still achieve 1. If we could do it without the 2, then we can still do it with the 2. We can also achieve a value of 2 by just using the value 2 by itself. Furthermore, as we go through the prior row and we discover, okay, we can achieve a value of 1, well, that implies that we can also achieve a value of 1 plus 2 is 3. All right? So by just using the single item value of 1, the only value we could achieve is 1. But now, by also using the item value 2, we can still achieve 1. Obviously, we can achieve 2 because that's our current item value. And furthermore, we can achieve 3 because that's equal to 2 plus the 1 that was true in the previous row. Then moving on, now we have our current item value is 4, so clearly we can achieve a 4. All right? But we can also still achieve all of the values that we could achieve not using the 4. And furthermore, we can achieve values using the 4 in combination with the 1. Okay, so to achieve a value of 5, we use 4 plus 1, which was achievable. Or maybe I should do this the other way. So looking through row 2, we can achieve a value of 1 from row 2. That means we can also achieve a value of 1 plus 4 is 5 using the current value of 4. We can achieve 2, so that means we can achieve a value of 6 by also using the 4. And we can achieve a value of 3, so that means we can achieve 7 also using the value of 4. And finally, considering our fourth item, whose value is 2, well, we can obviously still achieve all of the values that we could achieve not using this 2. And for the value 6 plus 2, we can achieve an 8. For the value 7 plus 2, we can achieve a 9. All right, so we can achieve all of the values except for 0 now by using these items 1, 2, 4, and 2. And once again, because we are now found that we can achieve the value of 9, we're done. We don't need to bother considering any of the other values in our multiset. We have proven that we can partition the multiset by creating one partition whose value is m over 2. And therefore, logically, the remaining unused items must also give us a value of m over 2. In terms of performance, well, as I said, this thing is really the knapsack problem. It's just a special form of the knapsack problem. And so its time performance is order of the number of items times the sum of all of the items in the multiset. Now, technically, we're looking for a value of m over 2, but these constant factors of 1/2 or whatever don't really factor into the description of the performance. So we just call this order of nm. M does not directly depend on n. M is really independent of n, and consequently this has what we call pseudopolynomial time, because one of the parameters is not dependent on the number of items that we have that we're considering. Alrighty, so that is that one.